Homework solution 2.10. Calculate the voltage and current in each device for the circuit given I of t equals 30 cosine of 1000 t amps. Also, find the apparent power absorbed by each element of the load and supplied by the current source. So we're given this circuit here, and then there's a little bit more information that's given to us in the time domain description of the current, and that is that the peak current is equal to 30 amps, and that the angular frequency of the sinusoidal signal is 100 radians per second. We are asked to find V, I, S, P, and Q for all of the sources. So I'm just going to use that as shorthand, that we're going to find them for all of them. So there's 4 elements. We're asked to solve for 5 different parameters for each of those elements. So the solution here is that we're going to begin by solving for the individual voltages and currents. So that's just a phasor domain circuit analysis problem that you're pretty used to. You can use any of the techniques that you already know how to use. You can reduce this circuit down to its Thevenin equivalent, solve for the voltage across this current source, use that voltage to determine the branch currents. So that'd be one method. I'm going to use a different method. What jumps out at me immediately is to use the current divider formula. I've got parallel branches, so if this was a voltage source, I probably would have used the voltage divider, but since it's a current, I'm going to use the current divider. So I know that the current through this element is proportional to the impedance of this branch divided by the total circuit impedance. So that's the method I'm going to use. To apply that method, I have to know the branch impedances. So I got to convert the henries and the farads over to reactances there. So I'm going to start by doing that. The capacitive reactance of a 2 microfarad capacitor is going to be equal to 1 over omega c. That's equal to 1 over 100 times 2e to the minus 6. And that's going to give me 5 kiloohms of capacitive reactance. X of L is equal to omega L, and that's 100 times 10, which gives me 1 kiloohm of inductive reactance. So I can determine total branch impedance of the 2 branches. I'm going to call that ZL and ZRC for the L alone and the RC branch. And so the total impedance of ZL is 0 plus J1K. So that's just equal to 1 at 90 degrees would be another way to write that. Then for the RC branch, I've got 4K, and then I've got 5K of capacitive reactance, so that's minus J 5K to account for the fact that it's capacitive reactance, and I'm just going to leave that in rectangular form, ZRC. So I'm going to now use current divider to determine the currents. The current in the RC branch, I'll call that IRC, that's going to be equal to the source current in its phasor form times Z in the inductive branch divided by the total Z of the branches summed, so that's ZL plus ZRC. So that is the current divider, and a similar current divider can be applied to solve for the current in the inductive branch. That's going to be IS times ZRC divided by the sum. So similar to the voltage divider, but a little bit different formulation there, so to be careful. If I want to know the branch current here, I actually multiply by that impedance divided by the sum of those 2 impedances. Remember, current divider works on parallel circuits where voltage divider works on series circuits. Okay, so we can just plug some numbers in here. IS in its phasor form is 30 over root 2 at angle 0 degrees. ZL we determined was, oh, I made a mistake there, that should be kiloohms, so it's 1,000 at angle 90 degrees, or J1000 would have been fine to put in there. Your calculator understands either. And then we just need to add those two, so it's J1000 plus 4000 minus J5000. And so you get an RC branch current of 3.75 at an angle 135 degrees amps. I'm going to repeat the process for IL. You've got 30 over root 2 at angle 0 degrees. We need to multiply that by 4000 minus J5000, circuit impedance of the RC branch, and then we add the two together. So again, we have J1000 plus 4000 minus J5000 ohms. And so that's going to give us an answer for the IL branch of 24 at an angle of negative 6.34 degrees. I wrote amps for that. That's actually, nope, that's right, yeah, amps. Right. So if you sum the two of those together, you should get 30 over radical 2 at 0 degrees amps. So that's all the currents in the circuit. Next, I need to determine the voltages in the different elements. The voltage of the supply, since the supply here is in parallel with this guy, the voltage here is the same as the voltage here. So Vs, I'll just say, is equal to VL. And I'm going to solve that by just saying that that's equal to the current through the inductor times Jx sub L. So that's 24 at angle negative 6.34 degrees amps times J1000. And that gives me a voltage of that source equal to 24,011.7 at an angle of 83.66 degrees volts. Similarly, the voltage across this resistor is going to be the current times the resistance, and the voltage across this capacitor is going to be the current times the capacitive impedance there. So we've got VR is equal to IR times R, and that's going to be equal to the current 3.75 at an angle of 135 degrees, multiplied by R, which was 4,000 ohms, and we're going to get 1500 at an angle of 135 degrees volts for the voltage drop across that resistor, and the voltage drop across the capacitor is calculated using I sub C times minus Jx sub C. So again, that's 3.75 at an angle of 135 degrees times minus J5000. And that gives me 18,750 volts at an angle of 45 degrees. So now I've got the voltages associated with all the elements. If I want to know the total apparent power sourced by that current source, it's just going to be equal to the current from the source times the voltage of the source. I'm using T just to stand for total right there. So that's 30 over root 2 at an angle of 0 degrees. And then I multiply that by VT, which came from right here, V source. I guess I should be constant, S to keep it constant. So 24,000, 11.7 volts at an angle of 83.66. Multiply that together, and I get 5.09365 at an angle of 83.66 MVA. So that's the apparent power supplied by the source. Sometimes this has a little problem scrolling. Okay, so now let's move on to the apparent power absorbed by the inductor. So we're going to use that same formula, IL star times VL. There's other ways to do that. You could use the magnitude of the current times the impedance, or the magnitude of the current squared times the impedance. We also happen to know the voltage now, so we could have done the magnitude of the voltage over the impedance using those different iterations of this formula, but I know both voltage and current, so I'm going to use complex conjugate of current times the voltage. And so the current flowing through that inductor we calculated as 24 at angle negative 6.34 degrees. I need to take the complex conjugate of that though, so I put a plus sign there. I invert the sign of the angle. So that is the complex conjugate of the inductor current. Now I need to multiply that by the voltage across the inductor, which was 24,011.7 at an angle of 83.66 degrees. And so if I multiply those together, I end up getting equal to J 5.76281 megavolt amps. So I could also say that Q equals 5.76281 megavar. Since this thing is purely inductive, S, the magnitude of S is equal to Q. So finally we wanted to know what the S in the RC branch was. And so that's going to be equal to IRC, the current in the RC branch, times VRC. And so that's going to be equal to, we come back up here, we've got IRC as 3.75 at angle 135. So its complex conjugate is 3.75 at negative 135. And then the voltage across the RC branch, since the RC branch is in parallel with the inductor, in parallel with the voltage source, its voltage is 24,011.7 at angle 83.66 degrees. And so that gives us a value of 56,2502 minus J 703,123, where that's watts and that is vars. So the that's all due to the resistor. That is all due to that capacitor.